All right, I want to have a look at the question we had for homework last night. It's a two-dimensional force problem. You can see it on the board here right now. It says calculate the net force acting on the object in the diagram below. Kind of similar to some of the questions we've done over the last couple of weeks. Kind of different from some of the questions that we've done over the last couple of weeks. We're looking for a net force. We know to find a net force, we have to add forces together. But this one, it's not quite as simple as saying, all right, 3 plus 4 is equal to 7. We've got a two-dimensional thing so that we know whenever we have that, we have to break it up into x and y components. Before we do that, though, I see one thing that tells me a place to start. Even if you don't know where you're going to go with this question, we all have a place to start. There's 5 words right now that tell me where I'm going to start with this. What are those 5 words? I don't like funny angles. We got an angle here of 30 degrees. We want to get rid of it. Even if you don't have any idea what to do after that, everybody knows that we've got to get rid of the funny angle. So let's do that off to the side here. We've got our angle of 30 degrees here, and we've got our hypotenuse of 20 newtons. Here's our x component. Here's our y component. We're going to say cosine 30 degrees is equal to adjacent over hypotenuse. X ends up being equal to, I think it's 17.32 newtons. And then we're going to say sine 30 degrees is equal to opposite over hypotenuse. Y ends up being equal to 10 newtons. There we go. We can, if we want, redraw that 20 Newton vector with a 17.32 newtons and a 10 Newton vector. And then we can just pretend this isn't here anymore. It's all gone. And what do we do at this point? This is almost exactly like what we did back in Unit 1 with displacement vectors. Remember we had those questions where it said, you know, Joe walks 20 meters to the north, then he walks 20 meters to the east, then he walks 20 meters at 30 degrees south of west. What's his displacement? Yeah, this is the same question, except it's Joe pushes with a force of 20 newtons north, 20 newtons to the east, and he pushes with a force of 20 newtons at 30 degrees south of west. We've got to do this the exact same way. The only difference is the units that we have here. So let's say x and y components. By the way, if anything canceled here, if anything balanced off, that would be a good thing, right? Okay, if let's say this 10 balanced this 20, which it doesn't, but if it did, that would turn it into a one-dimensional problem. And then we can just say F net is equal to the sum of the forces. Since they don't balance, this is why we have to do our x and y components. So what do we got for the x component? Well, let's go with this one first. The x component of that is 0. The y component is 20. Then it's this one. The x component is 20. The y component is 0. Then it's this one. The x component is negative 17.32, and the y component is negative 10 because it's downwards. Add these up, and we end up getting 2.68, and we end up getting 10 right here. So we're going to combine them. 2.68 in the x-axis, 10 in the y-axis, and this is going to be our resultant vector right here that we're going to find. Who's got the value of that resultant vector? Square root of 2.68 squared plus 10 squared. Digits. Ends up being, when we do the math there, 10.35, which we're going to round to 2 digits or 10 newtons. There we go. And the angle works out to be, well, it's the inverse tan function of opposite over adjacent, 10 over 2.68. What is it? Go ahead, Don. I'm sorry. 15 degrees, thank you. We would say 15 degrees north of east in this case, right? 15 degrees. It's coming from the east, but that's measured north from the east, so it's 15 degrees north of east, right? We did quite a bit yesterday. Hey, do you remember we did these problems where we had two-dimensional vector addition problems, but we also had other issues, other problems as well. That were a little bit more similar to what we've been doing over the last couple of weeks. I want to give you one of those questions right now just to see if you can distinguish between what we just did and then one of those questions we did yesterday that was kind of a cross between what we just did and what we did over the last couple weeks. Here's our wagon, our trusty wagon that we're doing our paper route with. We're pulling that wagon. Let's change it up a little bit. Pulling that wagon this time to the left and upwards at an angle of 60 degrees. We'd like to use 30. This time we're going to mix it up and use 60 degrees. Let's make the applied force here. Whoever's pulling it is going to pull it with a force of 50 newtons. There's going to be a force of friction of 15 newtons. And we're looking for the acceleration of this wagon. I'm going to have you work on this at your desks for a couple minutes, but I'm going to remind you before you do work on it at your desk, you're not trying to remember something that we did yesterday so much as think about what you know about this. Okay? And now, obviously, as you do that, you're going to remember things from yesterday, and that's a good thing. Okay, but we're not going to necessarily try to go straight to that. Okay, think about what you know about this and do what you know. It'll work out for you. All right, let's give it a shot. Sorry, the mass of this wagon is going to be 10 kilograms. So you need the mass, of course, to find the acceleration. You can find the net force without the mass, but we need the mass to find the acceleration. Okay, let's do this question. What do we see here? What do we see first in this question? Well, there's a couple things that we could see first, depending upon our perspective here. Okay, we see that it's a multiple force question, so it's going to be one of those F net is equal to the sum of the forces. That is if it's in one dimension, but we got an issue here with the fact that we have a funny angle. We got to get rid of that funny angle. Let's see if forces cancel out so that we can do it in one dimension, or whether we have to do it in two dimensions like we just did that last question. All right, let's get rid of that funny angle off to the side, and then we'll deal with that. We got 50 newtons as my hypotenuse here. This is 60 degrees. This is x. This is y. We're going to say that cosine 60 degrees is equal to x over 50. X ends up being equal to 43.3. Yes, 43.3 newtons. And y is the opposite side. Sine 60 degrees is equal to opposite of hypotenuse. Y ends up being equal to 25 newtons. All right, we can sub out the 50 newtons. We can sub in the 43.3 and the 25 newtons. Now, assuming this wagon isn't moving up or down, oh, sorry, we got one more force here we should label as well, and that's the force of friction. It's backwards here, in the opposite direction. Assuming this thing isn't moving up or down, what do we know about the force of gravity, the normal force, and the y component of that applied force? Yep, they cancel. Now, if the wagon ends up moving upwards for whatever reason, up into the air, then they wouldn't cancel, right? Or if it happens to fall through the ice, then they wouldn't be canceled. Okay, but assuming it's moving on the horizontal surface like it is here, then they're going to cancel out. Yep. But they switched. Cosine 60. Oh, I think you're right, actually. Yeah, I think you're right. I think I was doing 30 degrees in my head there. Thank you. So this is going to be 25, and this is going to be 43.3. Doesn't change the way we do it, but it obviously does change our answer, right? Thank you. So let's fix this up a bit here. 25 newtons and 43.3 newtons. So again, the y components still cancel out because this wagon vertically is in static equilibrium. And when it's in static equilibrium, it's not moving vertically and the force is balanced. So let's get rid of this and this and this. And I'm left with two forces, 25 newtons and the 15 Newton force. Let's say F net is equal to the sum of the forces. It's going to be, we'll call it the x component of the applied force plus the force of friction. Let's say the net force is m times a, it's 10 times acceleration. Remember, we always use the total mass. In this case, there's only one mass there, but in your quiz that you had a few minutes ago, there was, what, 3 masses? Okay, when you're saying mass times acceleration, it's always the total mass. Fx is negative 25. Ff is positive 15. Negative 25 plus 15 is negative 10. Divided by 10 should be negative 1.0 meters per second squared. So it accelerates to the left at 1.0 meters per second squared. Good? All right, let's try one more question now. One more question where we have a bit of an angle here, a bit of a F net is equal to the sum of the forces, a little bit of a similar question, but a bit of a different question as well. The question that you're going to see on the quiz tomorrow. That's our inclined plane question. So it's going to look something like this. Here's the hill. Maybe the angle is, let's say, 30 degrees. Okay, there's probably a pretty good chance that tomorrow's quiz will have an angle of 30. In fact, it does. I'm looking at it right now. It does have an angle of 30 degrees. Say we got a box on that hill. Let's say that box has a mass of 10 kilograms. Let's say you got somebody pulling it up the hill. Pulling it up the hill with a force, we'll say FA. It's 30 newtons. And the question is, what's the acceleration? I'll give you a second or a couple minutes to see if you can do this question. A little pre-quiz, a little practice quiz for tomorrow. Yes. All right, we kind of have a funny angle in this one, but we know that we resolve this one in a little bit of a different way. This one we're going to say, we're going to draw that free body diagram first and then deal with the angle. This is our force of gravity, and as I walk around and watch what you guys are doing, lots of people are drawing it correctly, but lots of people are still drawing it not quite correctly, right? That force of gravity is straight down, okay? It's not down like this, okay? It's not like this, it's straight down. Force of gravity is always straight down. The normal force is always at 90 degrees to the surface, so this is going to be Fn. And F parallel, combined normal force and gravity, is always parallel to the hill. Right? We draw this force right here, exactly parallel to the hill, okay, and then we just draw it over here a second time. It's not like we got two F parallels. We're just drawing it in two different places, that's all. Let's get the value of F parallel. And that's going to be, again, how we're kind of resolving this vector, how we're dealing with this funny angle, a little bit of a different way, right? We're going to say sine 30 degrees is equal to opposite F parallel over the hypotenuse, or we're going to say F parallel is equal to 10 times 9.81 times sine 30, which is 49.05 newtons. So let's label that. 49.05 newtons to the left and down, and then the applied force is 30 newtons up and to the right. Somebody was asking me as I was walking around and as they were working on the question, do we make that 49.05 negative? Sure, make it negative. If you do make it negative, make FA positive. You could make it positive, but if you did that, then you need to make FA negative. So we're going to say F net is equal to the sum of the forces. That's F parallel plus FA. F net is 10 times the acceleration equals negative 49.05 plus the applied force of 30 newtons. We're going to say negative 19.05 on the right side divided by 10 is negative 1.905. We're going to round that to two digits, negative 1.9 meters per second squared. So 1.9 meters per second squared down the hill. How many people got that? Okay. Those of you who got that should have no issue whatsoever getting 100% on tomorrow's quiz, right? If you didn't get it, make sure that you know what you're doing so that you can get it. Come and see me, schedule it up for lunchtime, and we'll fix it up for you.